Hi guys, welcome back to my channel Programming with Pirai. In this video, we are going to see about Leetcode question number 236. Lowest common ancestor of a binary tree. Given a binary tree, find the lowest common ancestor of two given nodes in the tree. What will be the lowest common ancestor? So it is defined between two nodes P and Q as lowest node in T that has both P and Q as descendant, where we allow a node to be a descendant of itself. So it signifies like we want to find the lowest node that has both the P and also Q as the descendant. Okay, what it signifies, let us understand. So if I give you a P and Q as 6 and 7, okay, where is 6? 6 is here, where is 7? 7 is here. So I can say the lowest common ancestor is this 5, right? Okay, you may tell that this 3 is also the common ancestor, right? Because from this 3, both the 6 and 6 and 7 can be constructed. Like means what? It is a descendant, right? Descendant for this node 3. Now, what is node 5? This 6 and the 7 is also a descendant, right? But if I tell you that for all other node, the 6 and the 7 is not a descendant, right? So I can say these two are the common ancestors for this 6 and 7. Upon this 2, I can say this 5 is the lowest common because this 5 occurs after this 3, right? It is in a depth. So I can say this 5 is the output for this P and Q value, right? So what's the output? It is 5. Can you understand this? Okay, now let's move on to the next example. It is 5 and 1. Okay, where is 5? Here is 5. So here is 1. So what is my answer? My answer is what? 3. So 3 is the lowest common ancestor for this 5 as well as 1. So from this, I can say that the path or the point or the node from which we are splitting into two parts is the lowest common ancestor, right? Take for example, first we are at 6, right? And we are at 7. So from this 3, whether the 6 and 7 are split in left subtree and right subtree? No, both are in the left subtree. But if I am at this 5, just observe carefully, the 6 is separated to the left subtree, the 7 is separated to the right subtree. So from this I can say the first split where both the nodes went to the separate subtree is our answer, right? Okay, let us understand by another example. So it is P is equal to 0 and Q is equal to 4. So it is 0 and 4. Now, what is the lowest common ancestor? I can say the lowest common ancestor is 3. From 3 only, this 4 is split to the left subtree and this 0 is split to the right subtree. So I can say what is the answer? Answer is 3. Fine. Now let us understand the last example. It is 5 and 4. It is quite different. See here, 5 is here, 4 is here. This 5 itself the ancestor of this 4. And then I can tell this is the ancestor of itself. So I can say what is the output? My output will be 5. Hope you understand this, right? Okay, how to do this? Okay, in simpler way, what I told you in the first itself. In first itself, I told you that we want to take all the common path, right? I will take the common ancestors and I will take the latest ancestors or the lowest ancestor, right? Okay, how we can take it? Okay, let us understand by using this example, 6 and 7. Okay, what is the path of this 6? I can say 6 path is this, right? Okay, what is the 7 path? I can say this is my 7th path, right? Okay, from this, let us write this below. So 3, 5, 6 here, 3, 5, 2, 7. Now, listen carefully. I will place a pointer here and I will place a pointer here. This both are what? Same. Okay, now go here. This both are what? Same. Okay, now go here. This both are what? Different, which means what is my answer? My lowest common ancestor is what? This 5. So my output will be what? 5. Can I understand this? So this is the brute force approach. What is the time complexity? I can say my time complexity will be O of n because in worst case we are just allowed to go to the entire 3. Okay. Now, what is the space complexity? It is O of n because we are using what? Auxiliary space. The array. We are using an array to store this, right? To store the path, right? So this is the time and space of the analysis. Can we optimize it? Little. Can we optimize it? Okay, let us understand by taking example. Now let us take this as our example 3. Now, P value is 6 and Q value is 7. Okay. Now, just tell me what is meant by lowest common ancestor. So, recently we have studied what? A lowest common ancestor is something in which the node splits the P value in one side and Q value in another side. It may be in left subtree or in the right subtree, right? So, I can say the node that has P or Q value in its left subtree and also the P or Q value in the right subtree is the node that has the lowest common ancestor property, right? So from there, I can say, I want to go to the left subtree. And I want to check whether P or Q value is present. I want to go to the right subtree and check whether P or Q value is present. If this is true, then I can say that should be my answer, right? That should be my answer. That should be my answer. Okay. How we can do this? We can do this by going to the term and checking above by returning some node value. Okay. I will demonstrate that. See here. So we are going down, right? So it will be what? A post-order traversal. First we are going down, then we are doing something, right? So it is like a post-order traversal, going down. Now, see here, left, again left. It is what? A null. But before going to this, whenever we are going down, we want to check whether that root value is equal to our any P value or Q value. Okay. Let us find whether this 3 is equal to our P value or Q value. No. Okay. Go down. Whether this 5 is equal to our P or Q value. No. Go down. Whether this 6 is equal to the P or Q value. Yes. Then I can say this should be one of my descendant. So I will written what? A 6 here. Can you understand this? Okay. Now it's time to go to the right side. Whether this 2 is equal to the P or Q. No. Go to the left side. Whether this 7 is equal to the P or Q. Yes. So I want to written what? The 7 here. Again, I will go to this 4. This 4 is equal to the P or Q. No. Go to the left side, it is null, so return a null. Go to the right side, it is null, so return the null. Now, tell me whether this 4 should return anything. No, this 4 should return what? A null. You may ask why. Because this 4 don't have any values or any node that is a descendant, right? Now, for this 2, what should I return? See here, my right subtree returning a null, but my left subtree returning a 7. So, it is saying that hey, you didn't split those 2 P and Q values, but you consist of one either P or Q. So just return it. So it returns what? As 7. Now for this 5, what should I return? So just observe here. My left subtree is returning 6 and my right subtree is returning 7. So both are not returning a null. Those 2 are not returning a null. So I can say I want to return this 5. Why? Because from this 5 only, the 6 is splitted and the 7 is also splitted. That's the meaning of this, right? That's the meaning of this return values. Okay, so I return this 5. Okay, now I'm going to here. Whether this 1 is equal to P or Q, no. Whether this 0 is equal to the P or Q, no. Go to the null, return null. Go to the null, return null. Okay, now here also it returns null. Go to the right. Whether this 8 is equal to the P or Q, no. Go to here, it returns null. Go to here, it returns null. Okay, for this 8 also it returns null. Okay, now see here, these both are null, right? These both are null, and also this 1 is not a property. So I can say it also return a null. Okay, and see here, my left subtree is returning 5 and my right subtree returning null. So I can say from this, I want to return a 5. Yes, so I got an answer. Can you understand this? By doing this method, how we can optimize our space and time? See here, our time will be remains the same, walk n only, but our space will be what? Walk h. H is the height of the tree. Okay, because we are using a DFS traversal. We are using a recursion stack. So this is the time and space of the analysis for the second approach. This is the optimal approach. Okay, let us try to understand the code. See here, first of all, we want to do what? A DFS traversal. So I am taking a function to do the DFS traversal on the root. Okay, now, what is my condition? Okay, if my root is become null. Okay, if my root is become a null, then what should I do? I should return the root, right? Okay, I will return the root. So return the root. Okay, and also if my root is equal to P or Q, then also I return the root, right? So instead of doing this, I will input that also. So or my root is equal to P, or my root is equal to Q. Then what should I do? I should return my root. Can you understand this? Okay. One step is clear. Now, what is this next step? We want to go to the bottommost. So it is a posterior traversal. In posterior traversal, what we do? We will take the left and right, right? Okay. Let us take the left subtree as dfs of root dot left, and then the return value will be stored in L. That will be useful when we are taking this value, right? That will be useful in our future case. Okay. And right will be what? dfs of root dot right. Okay, fine. Now, what should I do with this return value? Okay, if L is equal to null, what it signifies? It signifies, see here, my left subtree is returning null. So there may be a possibility of right subtree is not equal to null. With null, if it is null, we want to return null only, right? So directly I return what? Directly I return right subtree value. Okay, if right subtree is equal to null, then what should I do? I should return then left subtree value. Okay, if both are not equal to null, then what should I return? I should return the root. This root is our answer. Okay, so this is the whole code, and we call this function. That's it. Okay, so let us understand this code, and we can code it in the compiler. See here. So dfs of root, and I just done the same thing I written on that, and I included else alone. Okay, instead of this, you don't want to include this else also. And I'm just returning what? The function call. Let me submit it. Yes, it is submitted fully. Thank you.
Nice, Carol.
And the other hand, the dad,
Just so the name,